grade. Welcome to Science on Tap. I'm Linda Deck. I'm the director of the Bradbury Science Museum. And this is just a great time to get together, especially with all the students come back and in town right now. So let's hear it for our students who are here. Yay! Tell all your other friends. We want to see more and more and more. So Science on Tap is a place where you can come to learn from the scientists themselves about the latest cool research that's going on at Los Alamos National Laboratory. Science on Tap is a program of the Bradbury Science Museum, which is the museum of the laboratory. And we also do this in conjunction with the Los Alamos Creative District. And to tell you just a wee bit more about the Creative District, I'd like to introduce Rose Evans, also Mrs. New Mexico. I've just got Rose is the curator for the Creative District.
Hi everyone. So, like Linda said, I'm the curator of the Los Alamos Creative District. We are a program of the Los Alamos Commerce and Development Corporation, and we host On Tap in conjunction with several organizations through town. Science on Tap is in partnership with the Bradbury Science Museum, as she mentioned. We also do Nature on Tap in coordination with Pete, History on Tap, and Art on Tap in coordination with the Art Center. And so every other Thursday, you can come out and experience one of these talks. Science on Tap is always the third Thursday of the month, and then we rotate Art, History, and Nature on the first Thursday of the month. We also do the Tuesdays at the Pond series during the summer, so that's happening right now every Tuesday at 7 o'clock at Ashley Pond. Come out and see one of our concerts.
It was great Tuesday.
Yeah, it was really fun. If you missed it, we had a group singing about all kinds of things, sausage and cheese and lemurs and streets named after them and everything you could possibly think of under the sun. So you can check out the entire schedule for both On Tap and Tuesdays at the Pond at creativelosalamos.com. That's the Creative District's website. You can also reach me if you have any questions about anything else we've got going on. I'll let Linda introduce our speaker.
Thank you, Rose. Thanks very much. Appreciate it. Just to explain a teeny bit more, the Creative District is our version here in Los Alamos of an arts and culture district. We wanted to expand it beyond arts and culture, which is usually what you think of in a district, because we find science and engineering and technology a very creative, and math, a very creative endeavor indeed. And so we've expanded what we do to that. So I want to thank right now Uncork for hosting us. Thank you. Many of you have patronized them already. Feel free to do it again during the talk. This is very informal, and we really appreciate them making their space available to us. Before I forget, please turn off your cell phones or silence them. And my lovely cohort, also named Linda, has put on the tables here comment forms. We really do like to hear back from you what you liked about today's talk, or what else you might like to hear in the future, or give us any other suggestions you might have. That will help us. So the next Science on Tap will be, of course, the third Thursday of July, which is the 20th. Our presenter in July will be Galen Geisler, who's an astrophysicist with the laboratory's X-Theoretical Design Division, Integrated Design and Assessment Group, and he will talk about the upcoming total solar eclipse, which will be visible at many places across the western U.S. So we'll give you time to think about that and prepare to see it, because that eclipse will happen in August. It isn't going to be total right here, but I have a lot of friends that are traveling to where it will be total so that they can experience it. So we'll hear more from Galen about that. So here's how Science on Tap works. You've already done the couple most important things. You came tonight, you got yourself something to drink, you're settled down. That's great. So now we're here. We will hear a brief introduction from our speaker about his topic of expertise, something cool that's going on that he would like to raise our awareness about. And then we open it up for questions. And it's not just questions of our speaker. This is a conversation. I hope we all will have something to input, and very frequently we do get people who throw out things and somebody else says, oh, I remember this over here, and so it becomes more of we're all helping each other learn about the topic. So let me introduce tonight's speaker. Jeff Reeves is a fellow in the Space Science and Applications Group at Los Alamos National Laboratory. Dr. Reeves earned his Bachelor's of Arts from the University of Colorado in 1983 and his PhD from Stanford in '88. Since then, Dr. Reeves has worked at Los Alamos studying the space environment, its effects on satellites, and the applications to national security. Dr. Reeves is considered an expert in space weather, the field that studies how solar activity produces changes in the Van Allen radiation belts and near-Earth space environments. His current satellite missions include the Van Allen storm probes and the magnetospheric multiscale mission, and he's currently working on a proposal for a new rocket experiment. Another interesting thing that I learned, radio personality and station manager out at Stanford when you were a graduate student out there. He also has been brewing his own beer since 1986. Huzzah! And he's preparing to take a bunch along with him on a 3-week rafting trip down the Colorado in the Grand Canyon that starts tomorrow. So, Jeff, come talk to us now. Welcome, Jeff.
Thank you for that great introduction. Maybe I should start out, say, we should have a vote. How many people want to hear about space weather and how many people want to hear about brewing beer?
Or the Colorado River.
Or the Colorado River, yeah. You have to invite me back for those. That's a different on tap, I guess.
History on tap.
Or
The
adventure
history of
on
it.
tap.
Yes, perfect.
Yeah. So thank you all for coming out. It's great. I have not actually even been to one of these events before, so this is a fun learning experience for me, and I was advised just to sort of take things as they go, so I can talk a little bit about what it is that I do and maybe some of the things I don't do or shouldn't do. But interrupt as I'm talking. You know, you don't have to wait for the end of me because, you know, people have died of old age waiting for me to finish talking. Even about space weather. So, I guess I should start off with saying, you know, where does space weather fit into the cosmos of research? So space weather is kind of a subtopic of space physics. So you won't find anybody that has a job title of space weather person, but you will find people that have title that they're a space physicist. And one of the things that I often get asked is, well, so what's the difference between space physics and astronomy or astrophysics, that sort of thing? And essentially the distinction is that people that call themselves space physicists study things that are primarily in our solar system. And people that study things outside of our solar system are astrophysicists or cosmologists or what have you. You know, it's a little bit splitting hairs, but the difference really comes from the techniques. That one of the things that's great about studying stuff in our solar system is we live here. So we can actually send probes to some of the things that we're studying and measure them directly. And astrophysicists, astronomers, they don't have that luxury. Everything that they do is remote sensing, and you try to infer what's going on out there based on a few photons that you manage to collect here. So that's the basic difference. We can go and measure the magnetic field around another planet. We can measure what's called the solar wind coming off of the sun, and we can measure how that interacts with the Earth's magnetic field. And that's all space physics. Then if you say, well, so what? What happens when all of that happens? Oh, thank you so
Oh,
much,
you're
Linda.
so welcome. Other duties as assigned.
Space weather is really more about what are the effects of these space physics processes on things that we care about. Power grid, navigation, what have you, communications. And so I'll get into a little bit of that, but mostly I'll probably talk about what space physics is, and a little bit about what some of the consequences are. So where should I go with that? Let's start with where does space weather start? Well, space physics doesn't necessarily start at the sun, but space weather starts at the sun. If we had the kind of sun, the kind of star, because of course our sun is just another star, if we had the kind of sun that the Greeks imagined, it would just be a perfect sphere that was, just unblemished and the real epitome of perfection. And you see this in literature and so on. People compare perfect things with the sun. And if that were true, I would be out of a job, because space physics would be boring, we would understand it all, there would be no space weather, there would be no effects on the Earth. But that's not true. The sun is very dynamic, meaning literally it changes in time, and it changes by huge amounts. So I suspect most of you have heard about the solar cycle or the sunspot cycle, which are almost the same thing. But sunspots weren't really known about until we started having the capability of observing the sun. And Galileo's attributed with being the first scientific observer of the sun, which isn't actually true, but he was the first one that really kept detailed scientific records about that. You can be your own solar observer super easily, or those of you that have kids, this is a fantastic thing to do. Or if you're watching the solar eclipse, and by the way, safety note, do not look at the sun, even during a solar eclipse. You can make a beautiful solar camera with a cardboard box. You take a sort of a longish cardboard box and cut a hole in the end, put a pinhole in the end of that, and there will be an image of the sun projected on the bottom of the box. And it's really cool. You can do this. It's like a half-hour activity with your kids, and you can say, that's what the sun looks like. Right now you can see the sunspots. The longer your box, the bigger the picture of the sun will be. But you don't need a lens, you don't need to focus it or anything. So I strongly recommend, if you're interested in anything I say tonight, that's a neat kind of thing to do. I've done it with solar eclipses. Sometimes, you can tell this is unscripted because I'm going in tangents, but sometimes if you look at the pattern that light makes on the ground through a tree, you get images of the sun, because the leaves overlap in such a way that it makes a few tiny pinholes. And those few tiny pinholes act like a pinhole camera, and they'll project an image of the sun. And so I've seen some great pictures. I maybe try to take some myself during the eclipse, but where people, during an eclipse, of course, the sun doesn't look like a disk, it looks like a part moon, right? And all of those little dots that you see on the ground normally underneath a tree look like crescent moons. It's super cool. So the sun's very active. It goes through cycles, kind of like seasons. But of course, our seasons are due to the fact that the Earth is tipped. So part of the year, the northern hemisphere points towards the sun, and part of the year we're on the other side of the sun, the southern hemisphere points towards the sun. That's why we have seasons. The sun has seasons because of magnetic activity. First technical word is plasma. Sometimes I tell people not I'm a space physicist, but I'm a space plasma physicist, just because it sounds cooler. And plasma is the Greek word, just means has form. So there's blood plasma, comes from the same root. Space plasma is a form of matter that is an electromagnetic form of matter. So we all know about solids. You heat them up, they turn into liquids. You heat them up, they turn into gas, which is more dissociated. You heat them up more, takes the electrons all the way off of the atom. And so now you've got ions and electrons. So it's a charged medium. And charged mediums, support magnetic fields, they support electric fields, they support electromagnetic fields. And so one of the things that makes plasma so different than gases or liquids is the fact that now you have to bring in all of the electrical equations when you want to understand the dynamics. The sun is a plasma. It's obviously it's hot, and it's mostly fully ionized, more ionized than certainly our atmosphere, although the top of our atmosphere is also ionized, which I'll get to. But the fact that the sun has a magnetic field and the fact that the sun is made up almost completely of charged particles, not neutral particles, means that all of the motion, all of the swirling around of what, it looks like a fluid, right? I mean, it looks like a blob of liquid, because the gravity is holding it mostly together. But it's free to slip, and if you take a fluid sphere and you try and rotate it, the center has to rotate a lot faster than the poles. And momentum doesn't like that. And so there's a force that's resisting that. And so on the sun, it doesn't rotate like as a rigid body the way our Earth does. Parts of it rotate faster and parts of it rotate slower. So the equator, even though it's going at a higher velocity, the period of rotation is a little bit slower than the period of rotation at the poles. So the sun has a magnetic field like the Earth does, and that's due to the fact that there are these currents going around. You make a current go around like this, it makes a magnetic field that goes up and around like a magnet. And this current that's going around on the sun has trouble maintaining that because the equator wants to slow down and the poles want to speed up, and so that starts making some currents that go around this way. And that then, the technical term is the moments of the magnetic field. The dipole moment is the main moment. That's the one we think of like a bar magnet. These higher order moments create other tiny little poles around the sun. And those tiny little poles bunch up extra magnetic activity and store energy. And like with most things, you store energy for too long, it wants to release. And those energy releases create these huge bursts of magnetic energy that propagate out into space. And when those hit the Earth, it does sometimes really cool things like make the aurora, the northern lights, sometimes really bad things like killing satellites. And that's where the space weather piece comes in. So the overall solar cycle happens because the sun, it gets this current going like this, and then the extra little ones go like this, and it gets all wrapped up, and you get more and more sunspots which show up because of this magnetic activity. You get more and more solar flares. You get things that are called coronal mass ejections, where it blows off a big piece of the solar atmosphere. And when I say big, it will be sort of anywhere between 1/10 and 1/2 of all of space, all of our space. So half to a tenth of the circumference of the sun. Not a huge amount of mass. You get one of these enormous coronal mass ejections, and it's about the mass of an aircraft carrier. But it carries a lot of energy. The solar wind normally blows, just the normal solar wind, the atmosphere of the sun just kind of expanding out across our solar system. It's about 400 kilometers per second. So just think about that for a second. 400 kilometers per second is pretty fast. These coronal mass ejections can be 4 times faster than that.